We've looked at the idea of benzene being relatively unreactive, and we've looked at the idea that it doesn't polarise bromine particularly well, and therefore doesn't react with bromine in the way that we'd expect an alkene to. So the question that arises then is, well, how can we actually get bromine or anything else really to react with benzene? And what we've got to look at here to understand this is a different mechanism. It's not an addition, it's actually a substitution, and we need an electrophile, which makes it electrophilic substitution. The mechanism for this is a little bit complicated, and it's something that we do need to know. It's really important that you understand this mechanism, because on an exam they might give you any electrophile, and the idea is that the mechanism is the same for every electrophile. It's just the formula of the electrophile which changes. And so I'm going to take you through with E plus as our electrophile. Now, the first thing you've got to ask whenever you see a mechanism is, we've got benzene and we've got the electrophile. Where are the electrons coming from and where are they going to? Well, our area of electron density is going to be this delocalized pi ring system here. Now, it's got a low electron density compared to an alkene, but it still has a reasonable amount of electron density. So if we put an E plus thing here, if we put an electrophile with a positive charge here, we can attract the electrons from here to here, and so the arrow goes in this direction. When we have done that, what's going to form here is a rather complicated intermediate, and it's important that you draw this correctly. We've started off with two molecules, one of which has a plus charge, so this intermediate must also have a plus charge. Where does it go? Well, the plus charge is kind of delocalized into the ring, but it's most noticeable around the area where we have two bonds here to the hydrogen, which was already there, and the electrophile, which we've added. So your plus needs to go here-ish. Importantly, the ring hasn't completely been broken. There's still quite a lot of delocalization there, and it's actually still delocalized from this carbon here to this carbon here, and so we're drawing a delocalized ring in as a U shape. And if you look at mark schemes for exams, you'll find that the mark scheme says if you haven't drawn that U shape further than halfway up, then they're going to mark it wrong. So make sure that your delocalized ring is actually pointing in the correct direction for a start. It should be always pointing towards where we have the substitution actually happening, but also that you extend it all the way from this carbon to this carbon, because that's where the delocalized ring is. So this is our intermediate that we've formed. We now need to form our product here, which is going to remove this hydrogen. It's a substitution. And so what we're going to do is we're going to break this bond, and we're going to put that into the delocalized ring there. Okay, so I've not drawn that amazingly. It's got to go back to the plus. Okay. So we're breaking this bond. The electrons from that are going into the ring. They're going to delocalize around the ring. We're going to form this, and the hydrogen is then going to leave as an H+. And that's basically the mechanism. That's what's happening. There are a couple of examples of this that you need to know, and all of them that you need to just know come with a previous step, because we still haven't discussed how we generate this electrophile. So the first example I'm going to look at is the nitration of benzene. And the nitration of benzene is aiming to add an NO2 group onto a benzene ring. For that, we need an electrophile. Now if that was E and this was E+, if that's NO2, the nitrogen should be connected to the bond there, then what we need is an NO2+. Again, where you put things is very important. The bond is between the carbon and the nitrogen on these two, so therefore the bond is going to form between the delocalized electron ring here and the nitrogen itself, and lots of the time you'll find the plus written kind of over here, and that's kind of misleading because the positive charge is actually on the nitrogen, so I tend to write it like that. In the exam they will mark you down if the arrow doesn't go to the plus or the nitrogen. They usually allow either way, but if you put them together there's no confusion there. So how do we form the NO2+? Well, we need to put certain conditions in place to form that, and what we're going to do is we're going to add nitric acid, and that has to be concentrated. And we also have to put in concentrated sulfuric acid. Once we've done that, what will happen is we will form some water as one of these protons comes off and joins one of the oxygens here and one of the hydrogens there. So we end up with HSO4 minus, and we end up with that proton there ending up over here with that one and that one, sorry, the hydrogen and the oxygen, to make water, and then what's left over is our NO2 plus. Now you could put the plus up there. I'm going to be consistent here with what I've drawn there. After the reaction's finished, we need to regenerate this, because this is acting as a catalyst, and all we do to do that is we take this H plus and we react it with that HSO4, and that regenerates the sulfuric acid as a catalyst. The next reaction I want to look at is the halogenation, and this works in pretty much the same way for whichever halogen you're using. Now I've chosen bromine here, so we're going to start with an electrophile which is a Br+, and we're going to then end up with a Br wherever we had the E. So generating our Br+, we're going to need FeBr3, and we call that a halogen carrier. And the halogen carrier is a term used for lots of different chemicals. You can just put iron in, you can put FeBr3 in. For chlorine, as we'll see in a minute, you can use things like AlCl3, FeCl3. Just remember one or two of them. One for bromine, which has bromine in it, and one for chlorine, which has chlorine in it, and it'll probably be okay. So what we're going to do here is we're going to take the Br2, and we're actually going to use FeBr3 in this example. One of these bromines is going to donate a pair of electrons to the ion, and then this bond here will break to neutralise the charge that creates on this one, and the upshot of that is that we will end up with FeBr4 with a minus charge and Br+. Now this electrophile is another example of one, like the previous one, that we say is formed in situ. We can't just get a flask of Br+, we have to actually put these in so that the electrophile forms in an instant, and that's important because it has to kind of form right there, otherwise this reaction just reverses. We have to have all of these chemicals in the same place at the same time, but look, the mechanism's the same. Delocalized electrons in the ring to the Br+. The Br+ then forms this intermediate, same mechanism, everything's the same. The H+ is formed by the breaking of that bond there. The delocalized ring is formed, and we end up with H+. So the last step of this one is slightly different, because what we're going to do now is we're going to again regenerate the catalyst, the FeBr3, and we're going to do that by taking FeBr4 and the H+ over here again, and we're going to end up with HBr plus FeBr3. So we've regenerated the catalyst. Last one I'm going to show you is almost exactly the same. It's just this time what I want to make is chlorobenzene. Again, we've got Cl+ here, same mechanism all over again. This time we have to use a different halogen carrier which contains chlorine. So this is still a halogen carrier. Again, we're going to break this bond here. The electrons in one of these chlorines are going to donate to the aluminium. Going to break this bond here, and we're going to form a Cl+ as a result, and AlCl4 minus plus Cl+. and the Cl plus attracts the delocalized electrons, it forms the intermediate, the hydrogen-carbon bond breaks to reform the ring, and we end up with H plus. And the very last phase here is that if we take our AlCl4, which was left over here with minus charge, and we take our H plus from the end of the mechanism, we react them together, we end up with AlCl3 catalyst regenerated plus HCl. And that's basically it. You could, if you wanted to, put something organic on here instead of the Cl. So we could, for example, end up with something like this. We could put an organic group there instead of the Cl, and what that would do is that would form an organic electrophile. And if we had an organic electrophile, then we would end up with the R plus taking the place of the Cl plus in the molecule, and that's called alkylation. We're putting an alkyl group on the benzene. But everything works exactly the same way. As long as you understand the mechanism and you know the electrophile, you should be fine.